All right, so we've seen some simple examples of how we can model natural systems, things like wind or gravity and a bouncing ball. But one of the really interesting things that we can start adding to that is different kinds of behaviors. So having different objects, having different ways of interacting with their environment. One way you could do that in our bouncing ball example before would be to have different sorts of materials that bounce in different ways, either like bouncing higher or slower, things like that. Another thing though we can add is interaction between objects on the screen that simulate kind of like actual behavior of animals or people. And a really common and really cool one is called steering behavior or chase and flee. You can have things that are drawn to something or try to run away from something. And we'll see how we can use p-vectors to create those same kind of forces, very similar to how we're doing the bouncing ball example actually. So here are some tutorials that kind of cover this. I'll put links to these. You might want to check these out for more detail. So steering behaviors of different kinds. This is really common in games. So things like avoiding obstacles or chasing or running away. I think these diagrams are also really nice to explain that. This is another one from Game Sutra. This is so essentially, actually, this is really AI. This is where the border between kind of the coding that we've done so far in AI, there's kind of a lot of overlap here. This is very simple, but you could think about, how like ambient non-playing characters in a game might be following you or coming up to you or like going up and interacting with each other. Like how do you program that? And it's actually not that difficult. And then Daniel Schiffman's super great Nature of Code, always amazing book. I think this is a really amazing resource for anything related to simulation and natural stuff. It's free online. I'll put a link there too. His section on autonomous agents goes into a lot of detail on that as well. So you might want to check this out. And then lastly is this example where like people have been doing this research for a long time, and Valentino Breitenberg posited in was there a year here? I think in the 60s or something, around that time, this idea, he actually never built these vehicles, but he created this idea of these vehicles that would have different sensors on their front. Some of them would be drawn to light, some would be like avoiding light, and you can actually create these really complex, or he showed, you can create these really complex behaviors out of these really simple parts using, like this really simple kind of language of being drawn to something or avoiding something. And so in our example here, we're going to build this. We'll have three things, I guess. I'm calling them the player, which is this red dot that follows my cursor around, the chaser, who's the black dot who's chasing after me, and the blue dot who flees away from me. And they all do this at a different rate, and we can change that all. But the position and these forces are all defined by p-vectors, just like we've done in the gravity example. So let's go ahead and start coding this. There's going to be more steps to this than in some of the previous examples. So if you want to jump ahead, you can do that. But let's go ahead and just get my setup here. And just for convenience, I'm going to have it go in the corner. I'm also going to turn off the cursor because my cursor is actually going to be that red dot. I think that'll just be nice. So, and I'll just make my draw while I'm at it here. Okay, so let's start with the player. That's the easiest. We just want the player to always be located in the position of the mouse. So I'm going to create a p-vector called player. This will keep track of the player's position. And then in the setup here, I'm going to say player equals new p-vector. And I'm going to just start it at 0, 0. The minute I move my mouse around, it's going to go into that spot. And then my draw, let's shake it up. Instead of a dark gray background, which seems to be my usual, let's make it white. And then the first thing that we want to do is set the player's location. So I can say player.x. Remember, we can access the x and the y value from the p-vector using this dot syntax. So player.x is the x position. We can set it. We can also access it to do like if statements and stuff like that. player.x equals mouse x, player.y equals mouse y. And then we're gonna, and I'm gonna label these sections with comments. This is both good practice and as you'll see in a minute, there's gonna be a lot here, so it's gonna help us to keep track. And then let's make our player red with no stroke. And then since it's a circle, not an ellipse, we can actually use the circle command. Circle is relatively new, so my habit is to go with ellipse, but we can actually say player.x, player.y. And then let's make a value up here called diameter, because we're going to want to know how big each of these is to apply those forces. So then I'm just going to say diameter. And just like with the previous examples, let's test and make sure this works correctly before we go on any further. There we go. Our mouse has disappeared, and we've got this red dot following us around. So that looks cool. I'm going to, just for the sake of my eyes, I'm going to make this a little darker, but there we go. It has to be some kind of gray. Can't just be too much color otherwise. Okay, so we've got our player. That's really cool. Let's next make the chase. Oops. The V, it's a little hard to see with this font. V is capitalized in PVector. So chase, I'm going to set my player at 0, 0. Chase now, because that's not controlled by the mouse, that actually, the position really does matter. And I'm going to set them at width divided by 2, height divided by 2. You could put them wherever you want. And let's make a little space here. Let's go ahead and draw the chase as well, just so that we can see it, make sure everything looks good. So I'm going to say fill, and I think we did that as black, circle, chase.x, chase.y, and diameter. And let's just see. Cool. So our black dot, now obviously it's not doing anything, but we're able to see that this looks correct. So now we're going to add this chasing behavior, or our AI, to this, which is actually not that complicated, as we'll see. But let's go ahead and do this. Actually, so this is something maybe to be thinking about, is where, remember that processing any code executes everything exactly in the order that you tell it. And so it might be worth thinking about now, what order do we want to do things? Do we want to draw everything on the screen and then update? Do we want to update positions and then draw them on screen? Since in this case, we're controlling everything from the player, I think and the player is controlled by the mouse. I think what we want to do is set the player's position, draw it on screen, then compute the sort of forces for chasing and fleeing, and then draw those characters on the screen. I think, to me, that kind of makes the most sense. It maybe doesn't make a huge difference, but compute the chase behavior. So again, I'm labeling everything because this is going to get kind of complicated. What we're first going to want to do is figure out what's the direction, in sort of an angular sense, what's the direction between the player and the chaser. And this is where PVector math comes in and is really awesome. We don't have to do this ourselves. There's built-in functions to do this. So I'm going to create a new PVector called direction, and that's going to be pvector.sub player and chase. So this looks a little different than we've done before. If you remember, in the past, we did things like speed.add gravity. And this adds gravity to the value of speed. So it changes speed. In this case, we don't want to change the player or the chase positions. We want to get a new PVector, the direction that's the direction between them. And we just do that by subtracting one from the other. It's going to do both the x and the y. But the reason that we say pvector.sub is because we don't want to change the player or the chase. We want to create this new PVector called direction. And so instead, we can write it out this way, basically. So that's our direction. But this is going to vary. The direction, say in the x-axis here, might be 50 pixels. And here would be, our width is 800, so that'd be 400 pixels. And that's going to give us, a really wide range of numbers that are going to be harder to work with. Instead, what we want to do is convert those into a range that's always the same. No matter how far apart they are, we kind of want to know just the relative direction between them in the x and the y direction. And again, luckily, the PVector class has this built in using the normalize command. And what normalize does is it turns any PVector in any sort of range of numbers into a range between -1 and 1. So -1 in this case then would be in this direction. +1 would be in this direction, in the x, and the same thing in the y, and then any combination of those to give us any direction, which is really great. So we're computing sort of the distance between them in the x and y. We're normalizing that. And then but now in this case, then this would work just as it is, but the chase little dude would move really, really slowly because their speed would be between -1 and 1 pixels per frame. So the last step we can do is direction.multiply, mult is multiply, by some kind of speed. And we can create a variable for that. So chase speed, I'm going to put this up here. Again, that's going to be a float because we want to have kind of fine-grained control. Let's set that equal to 2. We can try changing that. Again, simulation is all about tuning numbers and seeing how kind of stuff changes. So we've figured out the direction, we've normalized it in a range of 0 to 1, then we multiply by the speed to get that change, and then we just say chase.add direction. So now we're updating its position based on this computed direction, and then we can draw the chase. So let's try this, and we can see here, it's always moving towards me because the direction between the player and the chaser is being computed, and then it's moved through space by that chase speed. And eventually when it hits me, the direction becomes 0, and so then the chase speed is also 0. You can see it's wiggling around a little bit because it's not super, it's not perfect, but it's pretty close. We can change this chase speed to be faster. So now it's going to come at me much quicker. Or you can make it slower, and you could like tune those behaviors. Chase speed also could be something that changes over time. So if you're making a game, for example, and you want the levels to get harder, you could make every level the chase speed increase, and that would be a way that you could do that. Cool. So we've got this working. Let's add the flee. And flee, now that we have chase, is actually really easy because it's basically the opposite. So let's say flee equals new. I don't know why I always like lining these things up. They do not need to be lined up. PVector. So that was at width divided by 2, height divided by 2. Let's make it width divided by 2, height. So we'll make it like a quarter of the way up. Again, let's just draw the flee fill. I don't know. We can make it a kind of a nice blue circle. And let's just verify. Yep, that looks good. So there's our flee. And then we can also compute the flee behavior. So this is going to work really similar. We're going to say, so we could compute the direction, and then instead of add here, we can subtract. So let's do PVector. So direction is already created, but we can say dir equals, so we could just use that variable again, PVector.sub player and flee, dir not normalize, direction.multiply flee speed. So actually, there's 2 ways that we could do this. We could subtract this direction so that it's going in the opposite way. But I think easier is to think of flee speed as negative. We want it to be a negative speed. It's moving away. So now my float flee speed, let's make it -4. So now, let's see, we can run this again. It's always running away from me. The blue guy is always going away because we're computing this and we're adding it every frame. And we might not want to do that. In this case, maybe we only want the flee behavior to happen when we've gotten within a certain range. That seems to kind of be more natural. So here is another great use of the PVector class that has some built-in functions. We can compute the distance between two PVectors, two locations on the screen, and then we can use that to kind of determine if we're close enough. So I can say float dist between, so the distance between them is player.dist flee. So this is the distance between the player and the fleeing object. And this is not a p-vector because distance is a single number. We call that a scalar. If we wanted to get the distance, actually what this is doing kind of is creating the distance between them. But we want it as a single number, sort of like at an angle like that. So this is basically the Pythagorean theorem. And then we can say if dist between is less than, say, 100, and we could try changing this number. Only then do we do the movement of the object. So now you'll notice flee stays in one spot until we get too close, and then it moves away like this. And it may not be obvious from just seeing this on the screen, but I have to tell you, it is so weird to be able to build things that feel like they have behavior, that feel like they have some kind of like agency or like decision that they're making just based on simple code like this. It's, I don't know, there's something really cool. There's actually not that much here kind of making this work, and yet we can create these sort of different behaviors. And in a second, in the next video, we're going to see how we can improve this to actually have each of these have complex behaviors where it might be chasing or fleeing depending on different kinds of conditions.